Here's an example on finding the equation for a power function from section 11.1 given two coordinate points, which could be pulled from function notation or it could be pulled from a table. But for this one, it's just two coordinate points. So on the right-hand side, I've listed some steps to follow for this method. So the first step is to make sure you can identify the 2 points that you're supposed to use. In this case, it's pretty easy. It's the x's are 2 and 3, the y's are 16 and 54. Just keep in mind which one goes with which whenever you go to do step 3. So once you have that, step 2 will have you take those xy coordinate points and make two separate power functions. So remember, the power function formula is y equals k times xp, x to the p power. So we'll take k times x to the p, two separate power function skeletons, and we're just going to simply plug in for the x and the y. So we'll get 16 equals k times 2 to the p, and then likewise 54 equals k times 3 to the p. All right, so once you have that, you're going to set up a ratio of matching formula parts. So like the left side of the equations are the y values, and the right side of the equation is the complete function. So I'm going to take those function things, and I'm going to put them in a ratio with each other, which is a fraction. And I'm going to put, it really doesn't matter which one you put where, but I'm going to put the 3 on the top, and then the 2 on the bottom. But just like in slope, as long as you keep the same order, it really doesn't matter which one you put on the top and the bottom. What does matter, though, is when you go to pull those values for the right side of this equation or proportion, this ratio fraction, that if k3 to the p went up top, then it's matching 54 needs to go up top as well. So I'll put 54 on the top and 16 on the bottom. Okay, so that's this set up a ratio of matching components where the correspondence occurs. So the next step is you just cancel the k's, because you can. K over k divides to 1, and you don't need them because it's going to be the same constant. And then rewrite, since it's 3 to the p over 2 to the p, you can rewrite that as 3 over 2 to the p equals 54 over 16. I'm going to simplify that, the 54 over 16, because you can, and then you'll be able to see easier what the power is. So 54 over 16, they'll actually both divide by 2. And when you do that, you get 27 over 8. And even though we wrote 3 up to the p over 2 to the p is 3 over 2 to the p, you can think of it as splitting it again. It would still put the same power to both of those numbers. So if you can think, okay, 3 to what power would give me 27, and 3 to what same power would give me 8? And the answer to that is a power of 3. A power of 3 cubed would give you 27, and 2 cubed would give you 8. So the p in this problem is a cube. Power is 3. Okay? So now that we found p, we're going to use that p function, or that p value, along with either one of the equations. It doesn't really matter which one. I'm just going to go with the first one that I made and plug it back in. So you have 16 equals k times 2 to the third power. Evaluate and now solve for solve for k. So 16 equals k times 2 times 2 times 2, which is 8. And if I divide both sides by 8, I get that my constant is 2. So now we have k. And then our final step will be to take everything that we've done so far, our p value, our k value, and actually rewrite our general power function for this problem. So y equals 2 times x to the third power. And that is the power function that is possible for the two given points of 2, 16, and 3, 54.